Morning, everybody. This is a embryology lecture. It is week 9. It's Wednesday. Sorry I missed class today. I got a bunch of doctor's appointments coming up. So best I can do. Some of you actually prefer this over the in-person stuff. So anyway, let's do some embryology. Today we're going to talk about folding, and then we're going to talk about Omphalocele. And these PowerPoint slides are uploaded on Brightspace. We all know this is not a pterodactyl, right? This is a bald eagle. In fact, it's a 4-year bald eagle. Look at the black on the tail here. Great. This is a very young Anna's hummingbird. Another Anna's hummingbird. Great. And where have we been? Remember last time we talked about differentiating the somite. Remember that the paraxial mesoderm turns into somites, little clumps of epithelial tissue that really represent almost a rudimentary spine for the little embryo. And they, in fact, the scleroderm, remember that, or the sclerotome actually morphs into the vertebrae. But this is what we did last time, and there's 4 embryologic tissues here that are important. So somite differentiates into 4 things. Somatocele cells, remember they migrated out just as this thing formed. We had sclerotome, myotome, and dermatome. Don't forget we have ectoderm on the top here, and there's endoderm on the bottom. And there really shouldn't be this big space. The author put a huge gap right here. This should all be filled in with this green mesoderm. And what would this be? Mesoderm, but what kind? Intermediate mesoderm. Probably to about here, and the lateral plate mesoderm would be down here. All right, but you can see this is already folded. It's not flat anymore. So that's what we're doing today. We're going to talk about folding. And yeah, there's our 3 regions and flat embryonic disc. We're going to fold it into a tube within a tube body design, which is our mature form. Starts about week 4. Classically, week 3 is gastrulation. Week 4 is folding. And so buzzword, tube within a tube body design. Yeah, we're tubular, right? We're rounded. We have a pelvic cavity, abdominal cavity, and a chest cavity, or thoracic cavity. And then we have, what's the tube within a tube? That's the alimentary canal. It's the mouth, esophagus, or pharynx, esophagus, stomach, intestines. Tube within a tube. So let's remember our parts now, because we're going to be talking about these again. You're going to be lost if you don't. You should have these memorized by now. But here's a head-on view, an axial view, or remember the AKAs for this type of a head-on or cut view? Because we're really looking from head to toe here as this thing matures. So hat, horizontal, axial, transverse, or you could say chat, cross-sectional, horizontal, axial, transverse, all AKAs. And here's our tissue. Remember there's our paraxial mesoderm, intermediate mesoderm, lateral plate mesoderm split into somatic lateral plate mesoderm and splanchnic lateral plate mesoderm. But we said if we combine these 2 regions, the ectoderm with the somatic lateral plate mesoderm, that gives us a new word. And that's somatopleur, aka somatopleuric mesoderm. And I know the AKAs drive you crazy. Drive me crazy too. So the splanchnic lateral plate mesoderm combines with the endoderm, this very bottom layer, to form collectively the splanchnopleur, aka splanchnopluric mesoderm. See how that works? All right, and so we're going to really focus on lateral folding, but here's kind of a oblique view from head to toe. So head would be up here. The tail of the little embryo will be down here. It's flat right now, but we're going to change that. Basically, you get a head fold and a tail fold where this comes under. So that's best seen really in a sagittal plane. So we can call that sagittal folding or cranial to caudal folding. And then probably more importantly, we get this folding of this side and this side. They fold under like these arrows show. And that's best seen in this axial plane, so that can be called axial folding or lateral folding, transverse folding, any one of those AKAs, cross-sectional folding, but lateral folding is typically the big thing. And what causes the folding? Well, the folding happens because this top layer, the ectoderm, grows faster than the endoderm. Endoderm barely grows at all, and this is growing laterally really, really quickly. So therefore the endoderm acts as a pivot point, and it kind of bends around, as we'll see here in a second. So what causes folding? Uneven growth of the flat trilaminar disc, specifically in this cranial to caudal plane. That's a sagittal plane. And then we have uneven growth in the axial plane, or horizontal, or transverse, or cross-sectional. Okay, that causes lateral folding, and we're going to look at that one first. So there's that oblique view, more of a head-on axial view with a little obliqueness in it here. So we're looking at this cut of the little human, and you can see, whoa, what happened to the flat trilaminar disc? It's completely folded over. And if we look at the blue, so the blue was ectoderm, look at how crazy much it's grown. So it would be growing out this way, but the green, the endoderm, hasn't grown at all. And so it bends around the endoderm. Or another way you could say it is, look at this amniotic cavity. It's grown like crazy, so the amniotic cavity growth is also kind of involved in this as well. But I like to think of it as the ectoderm has grown faster than the endoderm, and it's caused a bending because of that. Okay, and it's created these big old flaps right here. What are these flaps called? Those are called lateral folds. Okay, another way to look at it, if you use those two words again, if you use somatopleur and splanchnopleur, we can also do that. So we could also say that the somatopleur has grown faster than the splanchnopleur has grown here. So board question could go either one of those. So you got to know both of those. But these bottom layers don't grow laterally very fast. And the same thing is happening in the cranial to caudal direction as well. The growth is stunted, so you get a folding under that way as well. And here's a sagittal plane folding. So this is a view from the side, like this picture. And there's that big old, I think it's probably overdone here in this cartoon. Probably not this big, but there's a secondary yolk sac. There is you can see the connecting stalk has grown way out. We have a process. We're going to talk about the allantosis in a little bit. In birds and reptiles, that would be draining urine out of the urogenital system. But in humans, it doesn't. But we'll get to that. But sagittal folding is, you can see the flat embryonic disc has folded under from the head region and the tail region. Again, unequal growth of the ectoderm versus the endoderm has caused this. And it even moves the heart into the thoracic cavity here. Okay, but let's really focus on lateral folding. That's kind of the star of the show today. And again, we talked about this, so got a lot of overlap here just to drive the point home. The amnion is involved in this. We have an amnion. Remember, that was formed. That overgrows as well, but I think I pretty much covered it. Just kind of reviewing it here. Taking it a little slower. This is an intermediate step, so this is pretty fast. And now we can see ectoderm and somatic lateral plate mesoderm, or we could say somatopleuric mesoderm, or somatopleur is growing faster than these bottom layers. It's really as simple as that. And here's a little progression. It's getting more pronounced here. Now we got a problem in the middle of the embryonic disc because we got this big yolk sac. And we ultimately want to fuse these two ends together. These lateral folds need to come all the way around and fuse. But we have a problem here in the middle, as we'll see here in a second. So by the end of week 4, this is about all we're going to get here in the middle section at the level of the secondary yolk sac, which will become the umbilicus region. So lateral folding will be incomplete. This is a key point, note card point. Where in lateral folding, or you could say axial folding, where is folding incomplete? And that would be right here, where the secondary yolk sac actually gets pinched. Everywhere else, like out of the plane of the page and into the plane of the page, these levels will fuse together, but not here. So no lateral folding here. And this becomes a familiar structure, this kind of pinched off region of the secondary yolk sac. That becomes the Vitelline duct, and that should ring a bell. What does that ring a bell towards? Meckel's diverticulum. That's all about a Meckel's diverticulum. And we'll get to that when the time comes. See how that works. And yeah, we're creating a tube within tube body design here. And again, fusion is incomplete at the halfway point where the secondary yolk sac is. Just another little cartoon trying to help you visual learners. Just another look at it where we get folding coming around, lateral folds, creating a tube within a tube body design. Right, I think everything I said, a lot of repeats in these slides. Yeah, umbilicus will form here. We'll talk about that more in a second. Just to note again, the amniotic cavity is growing like crazy. When this fuses into the plane of the page and out of the plane of the page in this view, it'll make the pelvic cavity. So this will become the pelvic cavity, abdominal cavity, thoracic cavity, but not right here at the level of the umbilicus. Yep, we talked about the Vitelline duct is this part that's trapped. Yeah, and let's put it all together, what it looks like. So there's maybe a quarter of the way through week 4. We can see the amniotic cavity, however it works for you. Or you could say the ectoderm is growing like crazy, the amniotic cavity is growing like crazy, but the endoderm and this somatic lateral plate mesoderm is not growing. And so again, it pinches it here. Now this is our first cut right here that is above this level, like out of the plane of the page, where the secondary yolk sac would be not included in this cut. And now we can see what should happen. Notice these two lateral folds. There's one lateral fold, another lateral fold. They've completely fused together in the midline. See how that works? And yeah, and then we have a body cavity right here with a tube going through it. So this could be the thoracic cavity, it could be the abdominal cavity, the pelvic cavity. It can't be at the level of the umbilicus because the yolk sac stops folding in that region. So pretty cool. Just another look here. Another very cool shot. So we can see at the level, there's the secondary yolk sac. At the level of the secondary yolk sac, we can see lateral folds can't come all the way together. But above this, when I said out of the plane of the page, this is what I meant when I said into the plane of the page in that axial view. This is what it looks like. And we created all these new cavities. In general, you could just call them the body cavity, but eventually this would be the abdominal cavity. Pelvic cavity would be here. Thoracic cavity would be up here. What creates the body cavities? Lateral folding. Pretty cool. Bird break, our friends, the white-crowned sparrow. That's a mature one. Male and female look the same. All right. So what else does this make? Well, we kind of said this, but let's look more closely. So we created a gut tube. Right? So you tell me, where's this cut located? Is it at the level of the secondary yolk sac or not? It's not, because we have complete folding. The lateral folds have folded completely. And we have this structure, which has created a body cavity. So this will be the front of the human. This will be the back of the human eventually. We can see the crazy growth of the ectoderm. But we can see there's hardly been any growth. Even though it's fused on each side, the endoderm hasn't grown hardly at all. But it has fused, and it's created the tube within a tube body design. Really, you could say at this point, because of the amniotic cavity, we got kind of a tube within a tube within a tube design. But remember, we're going to get rid of this. This is the placenta up here. And so all these fetal membranes will be gone when the baby's born. So we'll just be stuck with the everything blue to inside. Okay. Dorsal aorta there, nodal cord, neural tube going on there. All right, so gut tube, I think we got that. But you should know, so what makes the inner layer of the gut tube? In other words, what makes the endothelium, the simple columnar epithelium of the gut tube? Most of the gut tube is simple columnar epithelium. What makes it? Where does it come from? This green layer, what was that? That was endoderm. So endoderm gives rise to the epithelial layer of the gut tube. The rest of the wall comes from what? Good. Splanchnic lateral plate mesoderm. Or you could say the entire gut tube comes from splanchnopleural or splanchnopleuric mesoderm, if you want to combine these two layers. See how that works? And then our body cavity here, let's just call it the pelvic, or let's call it the abdominal cavity. The intestines haven't formed yet. Just call it the body cavity. Just call it the abdominal cavity. What forms or what boundaries the abdominal cavity? What type of tissue? Well, we could say this layer right here, this red layer, would be the outer boundary. Remember who that was? That's somatic lateral plate mesoderm. And then the inner border would be this, splanchnic lateral plate mesoderm. So those are the boundaries here. And that's the space. The intraembryonic coelom really is the space that becomes this. And now we know where the 3P cavities come from, because this is going to morph into parietal peritoneum, and this will morph, all of this stuff will morph into visceral peritoneum. Or if we're in the thoracic cavity, this will be pleura up here. This will be parietal pleura, and this will be visceral pleura. See how that works? Let's meet the gut tube, all the parts of it. So it turns out there's a foregut, a midgut, and a hindgut. So we can see the tube within a tube body design from this sagittal view. We can see the heart is formed. We can see the lungs have started to form. So even the trachea going down into the tracheobronchial tree. Where's that derived from? We can already see it. It's derived from the foregut. So that's pretty strange, isn't it? The whole respiratory system is derived from the foregut. Same with the liver. The liver's a little different, but it's partially derived from the gut tube here, from the midgut region. But anyway, yeah. Remember the oropharyngeal membrane? Look where that's lining up with. That's going to be the mouth. Remember the hindgut or the cloacal membrane? That's lining up with the anus and the rectum that will form. See how this stuff is kind of coming together? Yep, everything we said. Gut tube opens cranially to the oropharyngeal membrane, the future mouth. Gut tube opens caudally to the cloacal membrane, future anus. Subdivisions, foregut, midgut, hindgut, we said that already. Let's look a little more specifically at what the foregut actually forms. So the foregut will give rise to the tracheobronchial, basically the respiratory system, the stomach, proximal part of the duodenum. So about the dividing point is the descending part or part 2 of the duodenum. So the part 1 is that part that connects to the stomach. Part 2 is the descending part, so about half of proximal part of part 2. And the liver and the pancreas all come from the foregut. Guaranteed test questions. High yield slide right here. What about the midgut? Well, that picks up from the lower distal duodenum, jejunum ileum, cecum appendix, ascending colon, and the proximal 2/3 of the transverse colon. So, and how are we, what's distal proximal? What does that mean? That's the way that fecal material moves through the tubes. So it moves up the ascending colon, goes across the transverse colon. We're going proximal to distal, goes down the descending colon, proximal to distal. So that's how that works. Hindgut. The distal 1/3 of the transverse colon, moving, following the poop, descending colon, sigmoid colon, rectum, and then some urogenital sinus, which will give rise to the male and female urethra. Okay, yep, the body cavities we mentioned already, but let's hit it again. So there's 3 divisions that this lateral folding gives rise to: pelvic, abdominal, and thoracic cavities. I've said that, but now it's in writing, so it's testable. What are the boundaries of these cavities? Said that already as well, but it would be the outer boundary would be right here. So that would be somatic lateral plate mesoderm. The inner boundary would be splanchnic lateral plate mesoderm, if you want to get technical. I mean, if you're not so technical, you could say somatopleur, splanchnopleur. I wouldn't write a question like that, but who knows what'll show up on boards. Yep, we talked about the 3 P cavities: pericardial cavity, pleural cavity, and peritoneal cavity, or peritoneal, tomatoes, peritoneal cavity. So the space in between the body cavity, that will become these cavities. So if we're talking abdominal cavity here, this will be the peritoneal cavity. See how that works. Anterior body wall would be here. So if I put a diagram on the test, make sure you don't choose this amnion here. Remember, the amniotic cavity is now completely surrounding the little human. So the anterior body wall would be right here. Okay. Let's see. Yep, we'll talk about omphalocele here in a second. But if this doesn't come together right in the region of the umbilicus, we can get some congenital herniations. We'll look at those here in a bit. So yeah, just another picture trying to drive this point home. You can see how we fused here in the midline and created these body cavities, 3 body cavities: thoracic, abdominal, and pelvic. Again, the umbilicus right down here, remember, that does not fuse, so we got a problem down there. But it's not open when you're born. We have an umbilicus, which is made of an umbilical ring and a plate, which we'll look at here. And just kind of a checkpoint, so we've made it pretty much through folding at this point. What's a 5-week embryo look like? So we're still inside the endometrium. A lot of text, if you're studying this stuff, they kind of forget. They just show you this picture without putting it inside the endometrium. So we're still in the endometrium. The uterine cavity would be out here. Okay, but we can see our little folded human. We could see the secondary yolk sac, connecting stalk. We can see how the syncytial trophoblast has developed like crazy. And some authors, not our chiropractic board books, other authors say that the syncytial trophoblast gets a little shell around it, like a condensation of this tissue. And they call that the syncytial trophoblastic shell. And we've already talked about villi formation. Spiral arteries have been tapped into. So chorionic cavity is still hanging in there. Amniotic cavity is hanging in here, surrounding the little human. So great. let's take a look at the anatomy of this area that doesn't close. So we have this, let's back up here, we have this umbilical cord that's connected to a placenta, which really hasn't completely formed yet, but we'll get a very developed placenta right here, which is where mom and baby connect with regard to blood supply and nutrients and such. And this is a kind of close-up of this connecting stalk. It's matured into an umbilical cord. And you can see we have these important 2 umbilical arteries and 1 umbilical vein going in here. But the point here I want to make is that there is tissue around that hole. Right here, lateral folding didn't happen. But we have some tissue layers. And these tissue layers are derived from some ligamentous structures like the falciform ligament, the round ligament of the liver, or at this point it's just the umbilical vein. But they kind of morph into this area and they kind of blend together into a umbilical plate in green and an umbilical ring there in red. And again, part of this is made from these structures, the median, right and left medial umbilical ligaments kind of morph in there. And then we have the urachus right here, which later in adulthood, or after the child is born, becomes the median umbilical ligament. Okay, we have the linea alba coming down, and that'll help form the ring at 12 o'clock and 6 o'clock positions. So this ring is important because herniations can occur through the ring or outside the ring, and that's the indifference. That's the difference between an omphalocele, which herniates through the ring, and the other one that herniates through the outside. But we'll get to those. The concept of Horton's jelly. So here's a cross-sectional view of the cord. And we can see there's our umbilical vein and our 2 umbilical arteries. There's the allantois, which doesn't really work. Again, in birds, it helps with respiration. It removes waste, and we don't have that in humans. But we do have these 4 structures. They're just not floating around in this umbilical cord. Like everything, like all organs, the parenchyma of the organs, which is the working parts of the organ, has to be embedded in something. And that something's called the stroma. And the stroma of the umbilical cord has a name. It's called Horton's jelly. And there's different layers of it, but we'll just call the whole stuff Horton's jelly. Talked about it. Let's put it in writing, though. There's the allantois. So about in week 3, even before folding starts, you get this little diverticulum that comes out. Some authors, like Carlson, says it's considered a diverticulum of the endoderm. Others don't. Others say it's splanchnic extraembryonic mesoderm of the secondary yolk sac. But you do get this divot going in, and this is the connecting stalk or cord here. And we'll talk a little bit about that, but that's where it starts, and it grows and it grows and it grows. And it actually will grow all the way into the umbilical cord. As we go back here, there it is. There's the allantois. And do they have it on this drawing? They don't have it on this drawing. But it would be, oh yeah, there it is right there. You can barely see it, but they have it labeled the allantois or allantoic stalk. So let's talk about it a little bit. Okay, we just showed you how it grows, and it grows all the way into the umbilical cord. So in humans, it doesn't give rise to urine. You don't move urine through it, even though it connects to the bladder, because there's the remnant of the allantois. The urachus is the ultimate, or the ultimate name for that. The urachus dries up and becomes the median umbilical ligament. But it still has some function in humans, and it does help give rise to random blood cells in the 3rd through 5th week as we're forming the heart and circulatory system. It helps form it's thought that some growth factors are derived from it that help form the umbilical vein and the two umbilical arteries. So it helps form those. Connects to the urinary bladder, but it doesn't do anything. It doesn't drain urine. But it ultimately becomes the median umbilical ligament. So the order of this is atlantois to urachus to median umbilical ligament. And that we can still see that in the cadavers. Ultimately degenerates into the urachus. Well, not ultimately, but next degenerates into urachus, and then after birth it turns into this fibrous cord called the median umbilical ligament. And that's clinically important because sometimes, like a ganglion cyst, you can get these random cysts forming in the body. Just a cyst is kind of it's a tumor, but it's movable. You can roll it. It's usually filled with a jelly-like material. But there are urachal cysts that form. And they're not dangerous. They don't become cancerous, but they can increase the chance of small bowel obstruction. And that's not a good thing. They can also increase the chance for omphalocele. So these urachal cysts or atlantoic cysts, aka, they increase the chance for omphalocele, increase the chance for small bowel obstruction. And we'll look at those again when we talk about Meckel's diverticulum, because a similar type of cyst can occur there. All right, some gross picture warnings. So if you're sensitive, don't go ahead because we're showing some birth defects here. Hernia, umbilical type hernias, omphalocele. There we go, right off the bat. So this little guy unfortunately didn't make it, but a great example of an omphalocele. All AKA is X omphalos. Pretty rare, seen, well, not in crazy rare though, 1 in 3,500 births, so they definitely happen. And unfortunately, about 50% of the kids with these things are stillborn, meaning they didn't make it. And it is a herniation. The key is, take home message here, it's through the umbilical ring. Exophthalmos, we said that's the AKA. The other defect we'll talk about is outside of the umbilical ring. Did I put a picture of that? No, I didn't. But we'll talk about that next time. But we'll focus on omphalocele right now. Okay, so the death, if the child does make it, or if it didn't make it, the death is usually secondary to obvious problems. Like that's the liver right here, so that's not going to be functioning right. The tubes, like can you imagine the hepatic portal vein trying to get into that? And the intestines get tangled, so small bowel obstruction occurs, heart defects can be in there, kidneys and lungs, they're all just kind of mangled and squished and they're not properly perfused, so that's why the death rate is so high. Some people do make it. So what's the etiology behind this? How does all this stuff get trapped on the outside? It's got to do with formation of the intestines. So strangely enough, when your intestines start forming, they grow faster than your abdominal cavity grows. And pretty soon they're out of room. And they herniate, naturally herniate out through the umbilicus, inside the umbilical ring. And that happens about week 6, and it's normal. And they mature out there while the abdominal cavity is growing and getting bigger. They mature and get bigger and bigger and bigger. There's a rotation that occurs that's important. But the key is, note cardable point, is they normally return back through the umbilical ring, back into the abdominal cavity by week 10 or 11. But week 10 we'll say just to keep it easy. And by week 10, the abdominal cavity has grown quite large. So it can accommodate these intestines even though they've grown. However, sometimes they don't get back. They don't get back through this ring. And we don't 100% know why that happens. We we believe that remember I said that the lateral folding usually doesn't close the umbilicus, it leaves it open. Well, if the lateral folds overgrow or grow too rapidly, they sometimes close off the umbilicus around week 9 or so. And if they close the hole where they came out, they can't get back in and they're trapped on the outside. What's that thing? That's the bare spot of the liver right there. Remember, the liver, most of it is intraperitoneal, but part of it is extraperitoneal, so it's outside the peritoneum. So yeah, sometimes they don't come back in, they're herniated, and that's called an omphalocele. Remember, the gastroschisis, that word was escaping me. A gastroschisis would be similar, but a gastroschisis occurs outside the umbilical ring, as we'll learn next time. Okay, this omphalocele, I always think of the O as the umbilicus, like there's the hole where they herniated, it herniates through that hole, because gastroschisis starts with a G. That's how I remember that. Cause, we don't know for sure again, but we think it's secondary to overdevelopment of the lateral folds, which basically crushes the umbilical ring so they can't get back in. Probably occurs in week 8 or so. And here's a recap of intestinal growth. So about week 6, there's the umbilical ring in green. The intestines are growing faster than the abdominal cavity, and they grow on the outside. And here they're really growing on the outside. And there's a twist that occurs. Great. By week 10 and week 11 for sure, but week 10 they start going back through the umbilical ring. And as long as the umbilical ring is open, no problem. They go back and form what looks like the intestinal system that we're used to seeing. But if the ring gets crushed, then we got a problem. They're trapped on the outside. Just picture that ring scrunching down by 80%. You can't get back in. Okay, another point here. Omphalocele has covering. Gastroschisis, which we haven't talked about yet, it doesn't. The intestines are more exposed, which is not good. But at least we have a covering here. So the amnion and the parietal peritoneum are taken with this. And this also, note, this does not occur within the umbilical cord. We can see the umbilical cord is cut way high in this one, as to you don't want to cut through these intestines. But that's another key note cardable point with the omphalocele. See how that works? So there we can see intestines. This one's not as big. The liver's still in the proper place. So this child is alive. And they don't all perish. Considered a congenital herniation, meaning from birth. Where I said this, herniated intestines go through the umbilical ring, covered by membranes, amnion, parietal peritoneum. Sometimes it can be more severe, and it's often not capable or compatible with life. When the liver is herniated out, we can't see the bare spots on the opposite side of this. Pretty tough to stay alive like that. I think everything we covered there. Just another look at it here. Yeah, sometimes they're difficult to see these things. And that's why when you're cutting an umbilical cord, you always cut it at least 5 centimeters above the abdominal wall, because you may have a very small omphalocele that you don't see. And if you cut it too close to the abdominal wall, you might cut the intestines, and the child will develop small bowel obstruction, infection, probably die from that. So you always want to cut it up high. Another possible theory of going back to cause, teratogens. So current theories think that, what causes the lateral folds to overgrow? We know the probable cause is overgrowth of the lateral folds, but what causes them to kind of grow too much? And it goes back to teratogens, cigarette smoking, maternal, secondhand smoke exposed to mom getting exposed to secondhand smoke, or heaven forbid mom smoking or drinking or doing drugs. There's all kinds of environmental toxins that that are teratogens. So somehow that accelerates the lateral growth and it blocks the return. Comorbidities with these things. So if the kid does make it, 75% of Omphalocele kids, they have other big problems. That's a huge chunk, right? Trisomy 13, other chromosomal abnormalities, Beckwith-Meuterman syndrome, extrophy of the bladder, where the bladder has developed outside the umbilical or outside of the abdominal cavity. So that's associated. So, of course, if these kids, you can see this with ultrasound, sometimes they have risk of death, obviously, fetal death. Typically, again, 50% don't make it. Premature deliveries occur. The old Cantrology of Cantrell, board favorite right here. Pentrology of Cantrell. It is a member of the Pentology of Cantrell. You should definitely know this. I'm testing you. I'm telling you right now, you need to memorize this. What's the pent? Pent means like a pentagon, 5. So there's 5 things. So a defect of the anterior abdominal wall at the level of the umbilicus. It should not be above, but at the level of umbilicus. Gastroschisis, omphalocele we talked about. We'll talk about gastroschisis next time. That's our thing right now. Hiatal hernia, a defect in the sternum where the heart is actually exposed or even on the outside. It's called ectopic cordis. Diaphragmatic pericardium, where the heart herniates through the diaphragm into the abdominal cavity. And then these are really common. Congenital heart defects, ASD, atrial septal defect, VSD, ventricular septal defect, ectopia cordis. That kind of goes back with actually that's one of them up here. So the other ones, patent ductus arteriosus comes to mind, tetralogy of flow, just listing some of the other congenital heart defects. So if the kid is born with a small omphalocele, be on the lookout for these things. All right. Having all 5 of these is really incompatible with life. So very rare. But having at least 2 of them is still rare. It's like Marfan syndrome, 0.01%. But that's kind of the prevalence of this. How about some parental signs of omphalocele or other members of tetralogy of flow? Alpha-fetoprotein. So that's part of a normal maternal workup. And they can test for it. It's a blood test. And it's not good if the levels are elevated. And these levels, it depends at what trimester you're in, because sometimes they're up certain level, sometimes they can be down, but an increased abnormally high alpha-fetoprotein is suggestive of omphalocele. So at the very least, you better get a ultrasound to take a look. Yeah, most of the time, abdominal ultrasound can catch that. And kids survive all the time. So if it's small, you just push the intestines back in and sew up the defect. You're not going to have a belly button, because the belly button gets pretty much destroyed in the procedure. But yeah, operation is successful as long as the internal organs aren't hanging out. You can fix these things. They tend to reoccur in adulthood. 25% of the cases need a reoperation, especially secondarily to small bowel obstruction. Anytime you open the peritoneal cavity, scar tissue can form, and that can wrap around the intestines and strangle it, cause a blockage. That's one of the acute abdomen signs that you will go into the emergency room if you have that. Well, there you go. So, testable material. See you guys next week.